Gonna be a short video dissing the AI systems. DeepSeek, ChatGPT. This is what I gave you. Only one simple question, but I'm gonna no trash talk you. I'm just gonna give you the answer. This is why I don't like using AI in this kind of point of view, because this is about some world, and little AI cannot measure it. Literally with its own eyes. Today's AI cannot do it, and it's not logical. It doesn't know what it's doing. It doesn't understand words in screens or anything. It doesn't have a reference that can really measure and get some meaning out of it. But I asked this question that I expect to understand because I expect to understand because it's like really a basic question because I've been feeling a lot of information already. But this is how the long text prompt was. This is from my 2 YouTube videos. This one, Muka OS, tomographic pi left polar lattice lapis. Basically it was a lapis. Lapis is like the area you're bound to the lattice. But this is more of a dimensional. This was the dimension. This is dimension bound, becoming dimensionless. Basically lapis is a lattice, but it's verifiable. It's an error variable. Basically, you can use an integration to verify a lattice, but derivatives can be a lattice, but basically what's the goal now? Okay, basically, let's go. Today's date is 29th of December 2025. The time is now 3:01 p.m. It's literally oh, here's this guy, here's Mush. Don't worry about these people. Disgusting. Look. I need to go. Literally. This is just discussing with my friends. These are the people I should be being with, like really smart people. Look, I need to go. But this is a lapis. So this lapis is like a lattice, but it's Oh, I don't have my alarm set. I don't have my alarm set, guys. I think I'll just get up and have my alarm set because if I don't have my alarm set, I will be wanking in bed. Because I got nothing else to do it. I can't person. But I'm black. This is me. So basically, a lattice is it's a grid, but it's not a grid. It's I gotta say, a lattice is basically Fourier. Let me just get up because this is kind of dark, and it's kind of dark, and I'm getting like a Fourier series. But let me get the Fourier series. Basically I'm trying to get the dimensions of it. So this is what I'm saying. This is a Fourier series. This is n to the power of a. So basically, this is the Fourier series I'm talking about. But you got the one here. Let me just make sure I'm getting it right. But I've said this already, but I've said it informally, so let me just address it formally, because, it has to be done one way or another. If I don't have to address it myself, I'll make mistakes along the line, because I'm doing my research myself. I'm building quantum computers, but I'm looking for a video on this Fourier series. But, I've already said this kind of thing is literally, it's not as easy. It's that, you gotta do it in steps. And that's what the Fourier series is. You can't rush the Fourier series. Because you lose a dimension. If you lose a dimension, the whole structure of step dimension, the step dimension, and that's what matters. Basically, I'm gonna go to the actual YouTube video, so we can address this problem of the lapis. So basically, how to compute a lattice.
In this video, we're going to talk more about Fourier series. And I first introduced the big picture back in my previous video on this topic,
so
and the link that is...
If f is a period 2 pi is a period. This is just like literally the same thing I was saying. It's like I understand this term word period is like let me finish Mush. He goes to a professor. I don't know Mush. I'm a professor, but I'm a PhD. I am PhD bound, but so basically this function of time grows takes an input a, but this input a is quadratic, so you just know it's quadratic already because it's input a. Basically got ax squared plus b y basically get the quadratic from this is called, so you see a squared b a squared a to the power of 3. B squared, it's a quadratic already because it's only got a squared term in it. It's a quadratic, it's a parabola, it's above to 2 and it grows exponentially at some point in time. And this was shown for time with 2 pi. So this is what I'm saying. This is easy to understand. If you get it wrong, you're getting something wrong. You're not wrong with you guys. It's just you are looking at it's some kind of basically, and there's nothing wrong with your angle. It's just you're not really understanding the problem. because you have to get some kind of meaning from it, and there's nothing meaning for it. So let me just address the Fourier series problem. So I want to just get up of this kind of thing because I just gotta do it properly because that's what this came to do. Because I have to do it properly. This is needed like right now. Like quantum. I'm being quantum computers. Hello, Mosh. I love you, Mosh. Mosh, you couldn't, Professor. I don't remember. I remember you, Mosh, but we didn't even get a YouTube. We didn't get a chat. Oh, anyway, Mosh. I'm gonna get yeah, basically, literally, it's here. Okay, thank you. Yes, basically, I'm trying to understand the subatomic world. Yes, basically, I'm really good with I need to understand small things. So, for me, I'm trying to do like the small things first because it's very more important than the big things, the scattered things. That's what I love to do. It's about quantum physics. It's like, control the bare minimum in human rights. And that's like my computer, Mook OS. It's not Mu1 OS. It's like the spirit of all evil and good and collections, both everything and nothing. Okay. Basically, I'm recording this video. I'm watching video. So basically, I hope this thing already goes through. So, because I got audio here, but I don't know what is going wrong. It still says it's listening to me, but I've got my headset on, so it should be still listening to me. So a function of time is equal to a0. A0 is the first term. The index term 0. It starts at 0. It goes this is index 0. This integration. If it starts at 1, that's the summation. Sum up. But a0 is just a term. The first quadratic term. But if you write the quadratic term, divided by 2 plus integration, the n equals 1. N is a natural number. When n is I can read about this solution, n equals plus 1. So the summation of n to infinity, a cosine nt plus n to 1 infinity sine. Basically, this is look, I don't want to explain this to you. Oh, but I have to because I have to bring it my way. So the kind of thing I'm saying is this is
down in the description. The idea was if I start with some function, like maybe this discontinuous function, this square wave that's 1 and then minus 1, I can try and approximate that function with a sum of trigonometric terms, a sum of sine terms and cosine terms. And as you can see here, this was the graph of the first 19 terms in some so-called Fourier series. It gives a pretty decent approximation, even with this crazy discontinuity that happens at the value of pi. Now, in this video, I want to answer a couple important questions. And the first of them is, well, how do I compute out what the coefficients in this Fourier series is? How do I figure out what the A0, the AN, and the BN is? And then secondly, we're going to answer the question, well, when does a Fourier series actually converge and become a good approximation? So we're going to talk about both of those issues in this video. Now, first up, I actually going to begin.
They're all destroyed because they are waves. They're destroyed because they are signals, and these signals are signals. They're just based on the imaginary units. And the surds, irrational numbers. If you are measuring something you don't know, you don't know what you're measuring, but you get a gap. But you measure something that comes from anywhere and everywhere. So that's kind of the problem there. It's like it's just waves, sound waves, anything that you're trying to get information from. There could be another codec format. It's literally the same thing as listening for answers in the universe. Where in a place where there's none, where you're gonna get at least the answers. So literally, I'm saying to you, the Fourier series is something
which is a kind of random seeming integral, the integral of sine of m times t multiplied by sine of n times t. And this is just going to be an integral that's going to be very useful to us. So how do I evaluate it? Well, it turns out it depends on the values of the m and the n.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done in a list view. Now,
if m is equal to n, then this is sine squared of m of t, and you can use a little trig identity, and I'll let you do it. It computes out and adds up to pi. If, however,
pi is the full one. There's no good operation. This is one axis. This is half an axis of integration, and this is why I really like my Lapis system. This is like 2 pi, but it does one full reversion, one full period, one full revolution, one full reversion. Basically, that's one full period. But that's in time, space, and time intervals. The period is just kind of acoustic. The period of time is a pretty short interval revolution. That's like wherever the full unit of what you're measuring. If you say in seconds. 60 seconds or 1 minute or 1 second or 60,000 milliseconds, you are measuring that unit for that time. And that's what period represents. 2 pi is just 1 unit. I don't like that 1 unit integration because it's just one bloop, one measurement you take, and it's not enough to get information in a to make a predictions. If you don't have the right enough information. So I like to take 2 derivatives. Let's see how he does this.
The m and the n are different. If you try to evaluate this using, say, integration by parts, again, I'll let you do the grunt work of it. It actually is always 0 if m and n is different. And the way I start to think about this is that if you imagine sine but with different frequencies, the multiplication with different frequencies always exactly cancels out. It always multiplies out to something that integrates to 0. So this is one of the most important little trig identities that's relevant for Fourier series. And there's a couple of them, because the same is true for cosine. Multiplication of cosine with different frequencies integrates out to 0. And if it's the same frequency, it integrates to pi. And finally, the last one I might want to consider is, what if I combine these two? Coses times sines. And this one doesn't matter about the m and the n. This one's always 0. Okay, so 3 different integrals, back to our original problem. We're going to use these in a moment. So, where were we? We were trying to make the claim that we had a Fourier expansion, that our f of t was going to be in some sense equal to this Fourier series. How do I find out what the a0, the an, and the bn are? Well, the first thing I'm going to do is I'm going to multiply both sides of this equation by sine of mt, and then I'm going to integrate from 0 to 2 pi.
So
I'm always allowed to do the same.
This is like a sine mt, the measurement of time, but I don't know. dt, I don't know what this means, but dt can be the delta time. But this is milliseconds times. But this is sine, basically. I don't know what mt stands for. But dt is delta time. I know that the derivative of time, or delta time, or the change of the time in time. It's just dt. You can call it delta time or just derivative of time. But you have to anchor it to that change. You can just have the kind of operator, but it's kind of and see what he's doing because it's trying to separate everything. So mt, I don't know, but so I don't just for me I just think more mt. But because I don't really see the notations on this side of the board or something. But this 2 pi is I can see everything working going for how this can become. Wait, can I? No. Let me check, because I know it's not correct. I don't know. Untouchable. But basically, you don't have to even know it's correct. The kind of mathematics he does is kind of advanced. You can follow his logic. What you can follow is the good part. And you can start to verify when you can get to the verification
thing to both sides of an equation. I can multiply by some other function, and I can integrate it over some region. I can do that. If its original is equality, then I get equality here too. Now, let's think about what's going to happen. The first thing I'm going to note here is that the contribution from the A0 part is going to be just nothing. The reason here is that this A0 is multiplied by sine, and when you integrate sine over its period, you always get 0. Integration of constant times sine over its period is again going to be equal to 0. Then I can look at all the cosine terms, and all of those are going to be 0 by that previous identity. The integral of a cosine times...
Don't know this very well. He understands the system he's modeling already. He understands what he's doing. He doesn't think about this. This is what people should be doing, because when they're doing mathematics, it's like cancelling out. It's cancelling out, but it's factorizing all the terms out. It is they don't really gonna be crunchy. But it's calculus, so you have to have this kind of things at some point. Because it doesn't matter whether you're doing polar series or not, or Taylor series. I don't even know what they are. But this is my one of Fourier series. Basically, the Fourier series are digital, they go in steps. But let's just see. My digital go in steps because it's like they even like after every angle. Every bloop is a signal, and that's a digital waveform that you measure. But the digital bits have to go in halves. Half of the because they are a quarter of each of the system. It's half and half for the tomographic layer. For example, they are little bound to tomography only because they are working waves. What I mean is like they work up and down, but they work in digital. But they don't work at as in basically they're analog signals, but in digital waves. Basically, because it's more. If you don't really understand what I'm saying. Let me give it to you in a way I understand. So you have a signal, and the signal is a static signal, like signal of a signal, everything. So you have a digital waveform, Never think about signal. It just goes right up, left, right up, down, or right up, down, all I said is right up down, right up down. But you know, you have to do this in some kind of frequency oscillation. Basically, it's just you have to do it in steps. But it's usually really compact. But you have to have some way to do it. So the thing is, you have to get it in half, each in half. Everything has to be in half. Put it there homogeneous only. That's to be one half. One half of data. That can be some kind of message you send in binary. But that would be but you have to put it as waves only because the waves have to go up. So as the amplitude goes up, you have to get the wave propagates up as well. Like, you know, you have to take steps of up. You know, half and half. Because you have to go like because they're working on oscillation, working on the field way in. They have to go. They have to behave like a field properties. They have to. So it's like they like this one and they go up and they go like this and it's like. But you know, that's what I'm saying. They go like that. It's like but they do have to do this. Have this area of the waveform that just the mean. This is what it looks like. So no matter how small you cut it, how small you measure, how much you send it, they go half and half. So let me just stop this because I don't want to do this today. But you know, this is what I'm saying. It's let's just see the full example here.
Okta secures AI.
So Okta AI, I love AI. I don't love it. I love my AI, but mine is not really so I don't really want to talk about AI. I don't like AI. I love AI when it works. I don't like it when I can't get it. You know. So for example, we got this square wave. This is square wave. This is square wave. You see this square wave? Dun. You know, basically, you see this height? There's just the integration of height. But this minus height is where it becomes 0. But this is square wave. This example, this is like a sine waves. Here different true sine waves. That makes it sine and cosine waves make this other function. Here, two different sine waves that are together to make a new wave. You know, this is this is a new wave. So the constructor was, but this is a wave graph. This is like a sine plus this. They make these two waves, making this wave. But this is a sine x plus 2x to make this wave. And this is this is coming. This is new information. Yeah. So this information is a new information that gets really these two. I'm gonna say this two work together. These signals are coherent. They can be together. And they work together. You know, that's what I'm saying to you. One take this square wave. So can we use a sine wave to make a square wave? Yes, you can. This is sine wave. This is sine wave. But this is square wave. So this is two sine waves. You can make a square wave. So you can make a. So the more square waves you get, but you can get square wave. So this is all digital. Square waves are like the digital characters. But you have other waves. You got basically how many waves are there? Wave types. One more thing. Because I got the answer. What I was looking for. Hello. Wave types. Masses from. Basically, I got this thing. Wave types. Introduce wave types. Waves are classified based on the mediums. Like, let's enter the point of waves is a medium. This is a wavelength. This is a incident wavelength. This is where we are. This is second Hammond. It's not where we are. I don't know. This is material under test. This is reflective. I don't really know. But this water wave, this is what we see. But this isn't probably in a house. This is like a C1. This is surface reflection. I don't really know. Basically, this is square waves, types of waves. Basically, go triangular wave. Yes. So basically, this is sine wave, this is square wave, and that's just one. But go to sorted wave. So basically, I got to try to implement another. But this is what I should do today. Let me try to get up a bed and do another video. But I'm trying to in the next video take one of this wave, a sorted wave, amplitude over time, and the triangle wave amplitude over time. Also, a wave combination of the sine wave and the square wave. So literally, have a noise start. A noise start definition. A noise start is takes a tomographic area. Basically, it takes the angles minus 45 degrees. Minus 45 degrees north northwest and north south. My friend is north south. The noise starts basically it takes the range measures that range on my phone twice once. That's your start area. Basically, any signal that proves in that field is now your own. It's like you are now starting the machine. It's like trying to find the ignition and you're finding when you know you jump start it. So this is jump start Q. This is just really you start a machine, can start your computer with this kind of frequency. So how you complete this now? I'm doing computer now. I don't really know how to start a computer. So let me just design one. The sine one will be this. 1 over sine x. No. Let me just use the master's phone. Let me use this graph phone. Let me use grapher now. The grapher will be this. So the graph will be this. So literally, it's like the summation of the sine waves is like a. So what I'm saying is, so I got my calculator here. It's like here. So we get an example. So what could always stop? Let's take the area minus 45 degrees. Minus 45 y over x. Y over x is the area. So pi r squared. Pi, well b. So the radius minus 45, basically, it's basically half of the radius is 4.5, but that's basically facing northeast. So this northeastern region, this is 0.45, but because it's northeastern, it's facing northeastern, northern, but north to the power of 4, north quadruple, because you get north, and that's really start and end. Because you can start on north and end it. We don't know where you are on the axis, so you have north to the power of 4, which is the full measurement of the axis. But to have a square area, that means you are 180 degrees, because that's really a Hamiltonian system. Like, it doesn't matter, or Eulerian system. So you can go from A to B and B to A, and that's what I'm saying. You start with the problem. So I'm trying to say, like, some kind of, to ignite some kind of start kind of system that you don't have any control to. You have to add noise to it. And that's kind of the thing. You have to have the area of noise so that you can start something. So you have to like bust the signal. If you get a signal, that's going to the noise. But I'm going to use the sine wave for now. But I got other ways to do it. So this is what I'm going to do today. 0.5 times pi. Zero 0.5 times pi. Pi will be pi divided. Basically, this is not good enough. Pi 0.5 of pi. And that would be good enough. Divided times 1, divided by 180. Because 180 is the characteristic of it. So this is 0.545 divided by 5. Will give me a range of pi r squared. No. So 0.545 times 2 will be 0.9. Now this is 90, 0.9. This would be 0.9. But this would be 0 minus 0.9. Divided by 180, but 180 is not the correlation. So I want to like because I'm divided by 180, I have the still state of 180. Because I don't want to destroy from 180. So we have to divide by 180 anyway, because let's go from 180 to B. This is the first start. I will get the area, but this is the area I'm facing. Divided by 180, because I'm facing one direction. So that will be divided by 180. 0.9 divided by 180 degrees. And that'll be 0. Basically the signal has to basically to relay 0.9 divided by 180 is 1. No, this is 180 as in no 90 divided by 180. This is 0.9. 90 divided by 180. No, 90 divided by 180 will be 0.5. So 0.5 in area. So if the job started in the system, with or without consent, I have to, with consent of course, I have to like send a sine wave, a wave that propagates in a medium of all sine, the kind of that propagates and the calculus is 0.5, 0.5 cubed, because 0.5 cubed. Basically, for each interval, I have to get the wave that just jumps. So this is like a start, but I execute it on the fly because before it's just added noise system. What is noise? Noise is definition by open system. So to start any system in an arbitrary state, in a known state, known state, they may know, or you may not be able to start up. You have to add noise. But noise means you are clearing the system's memory ahead of time. The state is in, the still state in it. The string stays still in its stability. Whatever the system already holds, it has to be cleared. And you send a signal of Fouriere series that will do this. 0.5 is 90 divided by 180, and that'll be 0.5. This will be half of it. So this is half of the signal of wave. So 0.5 is what I do. So you want to have a constant of 0.5, n.5. So like let's say we got this function here. So we get the y over x, the rise of run. But the secant is the SOCAM. So we got so you get the secant, which is the secant is the y over x. But you go to cosecant, which is the x of y. You won't be needing the cosecant, but you know what I'm thinking. So you get the cosecant, but literally you get the secant. Can I just type in secant? I hope I can just type in secant. I hope I can just type in secant. N times x. Let me see what this means. Nope, you cannot type in develop. It's like it's not as bad. It's like bad because it's like so sine over sine x. So basically, this is sine secant secant will be sine this will rise of y over y sine over cosine. So I just have to plug that in as I know it. If I don't know it. So this is a cosine here. Sine x of sine n of x is 0.5. But this is what the noise looks like. But this noise can be included or something. So you may think this noise is just noise that I add, but it's just starting. It's just say, okay, you're richest. I'm gonna give you some basically it's a buffer that you push into whenever you have a noisy stop, you add some noise and some buffer. Something the code can the system can remember, and this is just the secant function. So let me think. So basically, the secant is y around just like the standard function of it. But this graph is here is 1 to 10. I don't even know what 10 ratios are, but I'm ready for them anyway. But you see this thing is going up and down. See, it starts here. It starts here 1. It starts 0.1, 0.1, and it's like literally going up and down. So 1 to 10. 1 to 50, but you see the errors covers 1 to 5, literally. 1 to 5 is like a little, literally just up down. But you see what I'm saying? It's like sine n is just a natural number, n is 1 to 10, 1 to 5, or 1 to, let's say 1 to 2. See, it goes up and down, it's just like really just great. Let's go 1 to 20, because it's 20 is better, it's like but get to 2. 20, but get to 0.1 we get 1 to 20 because that's really easy to but this is like a step system. So this function here is just y of x, but it's not tomographic. So it's divided by the total radius. So this total radius is 2 pi, 2 pi. But 2 pi is too good, so you have to get pi. So divided by pi. Oh no. Divided by pi. I don't know how to put pi. Basically, this is like a 1 over pi. Basically, you send the you send the 1 divided by pi. Pi. I'm trying to give the times pi divided by pi times pi. So you get the inverse one. I can times by pi. Times the pi. The number of pi is just. So it's just big number here. 3.141536 now. And it's pi. I don't know what I'm doing anymore. But you get that's running over the unit model. But you get that there. So this is like a divided by pi, or the pi divided by basically this is pi divided by not pi by pi. Sorry guys. I don't like making mistakes here. So it's like a literally what I'm saying, guys. It's like a 3.14 divided by pi, and this would be pi. So this pi is like a too much for rare 1415. Because like the pi, but pi is a half pi. It's pi over 2. So pi is 180. No, this is half of pi. So this would be half pi. This would be divided by half pi. This would be a pi over 2. A pi divided by 2 would be, or square. Let's do the square root of pi because that's more easy for me to compute. It's just like sorry. So the square root of pi is half of pi. So you have to get. So usually this is half pi. I just think that's square root of pi because it's just 1.7724. 1.77245. 1.72245 times divided by this it would be literally 24 1.72. And this would be like a zoom in, zoom out, but like a literally. So this is these dimensions. It like it has a kind of oscillation, and this is this is how it's sort of pi. But this is divided by pi divided by itself. This is the half pi. This is like a pi divided by itself. It's this logically. This is the pi divided by itself. Pi divided what constant pi to what constant pi. But this is just check. It has some this space. This is like space. You see it's like axis. This can be integrated over. So we can take the integration of this and give it some the area. So let's get an integral calculator. I don't know. Because I look at integral calculator, I don't know what to get them. I don't know. Let me just put this in. Because I don't want to calculate the integral of this. So the integral of this is one of the first integration of this is 1 over 2 n the pi divided by pi, but it's like half pi divided by half pi, because I can make mistakes. Let me just try to get more precision after. So get 1, 2, 3, 4, 5, 6, 7, 8. 8. Just 0, 1. This is 177. But this would be calculated. This would be pi 10. 10. This is integration of 1 n dx cosine times 1 over n. But n is what? N is 1. N is 1. Just put n as 10, because 10 is a unit I was using before. What's 10? So this is a 10x. So this is so the equation of divided by 10x is like dx given dx. Go do calculator. It should fail. It will fail me. I know it will fail me. You open is so this is my input with decimals, of course. This is the kind of no additive can be found given the limit. Basically, you get it's kind of a thing. This is space. So this is the noise you add, and this is space you create around the noise, and this is where the noise really happens. So the noise is like the area here, but it's not a look up definition quicker like the same. So, x is what? What? I don't really do it now. So I fucked up really. So I should just make the n and x is like I really know what I'm doing now. This should work as intended. So literally, I put the values here. X is 1. But x y moves. No, x is 10. No, f of x is 1. But 1 to 10. X is 10. Oh, x is 10, and then w x y. This would be so this is fx dx. Hello, I love you. Check your answers. But this is 3 or 35 10 over x. This 10 over x is like a literally the expression, but it's like my input f of x, but I didn't put f of x as a value. No, this is half pi, but this is the expression of the one derivative, the third derivative. But it's meant to. Let's use some examples later because I don't wanna see what I'm saying. So this is my the one. This is the half pi divided by 2, but this is the kind of because it's gonna be half pi. This will be going clockwise. So I have to start clockwise, anti-clockwise. So I have to go from upper axis. This will be minus half pi. And this is the integration of this system here. So this is the what I'm looking for. The integration of the sine x, but the sine x is not used. So sine x, let me do some simplifying. But nx is one number, nx is number, nx is 1 to 10. But I don't see the summation of 1 to 10. I'm thinking I'm doing it wrong. Let me ask the AI to do it right. I don't really want to bother with this. So I actually to do it right. Write this mathematically. Write this. The simpler version is this, or more compactly this, but it's not like no. Need this. visible. On the right. So it says here, example input. Log m. So minus a cotan. Oh, this is like a cotan. So I don't have to like put it the way it did it. It's simple as to. But this is not or more compactly. Okay, so I'm now verifying this to be minus time cosine a times x divided by sine a times x. So it's not really that dx, but times dx dot dx. But x is the dx, the root of x. But I don't see dx here. No. Oh, this is the same thing as this. I've done it, so I've done. I've got this format. I'm happy. So let me just I could go with it. So this is going the opposite way, but it's going over the 180 mark. So this is your inputs is coming to stabilize this. But it's just one step into. Oh yes, I can get some input. This is what I'm saying, guys. So what I'm saying, I now get something to do. So what I'm saying, this is what I'm going to do. So I'm so proud I did this properly. So you get f of x, which is this function. But this is f of star of x. This is outside. So you get noise, and you get basically you will see lattice. So when you get one noise, that means you get option you cannot do in that state because you just want to every option to remove. Because you get noise, one noise, you get what we call noise start. So you get no signal means you don't get any information from the system you're starting. That's just gonna stay for everything. It's just off. It's just off. And you get no noise. So that means no noise is what you don't get any errors information that relays some kind of a mishap or errors they call them or corruption. Whether it comes from computer, mechanical, digital, from any digital system. Literally. So you get that kind of system. You get digital which is noise. You get noise, no noise. Obviously, that means notice you don't get any kind of because it's like the framework of testing, roof test. So you get no signal. No signal means what? You get no input to that system. That system is close to you. But it's open someone else or allowed to so many people. And get no noise. No noise literally just means there's no noise out of that system. In and out of that system. There's no kind of ambiguity in getting. It's just like there's no undefined in C specification. It's just everything is defined and everything is the perfect world and we live in harmony and everything is just working as intended. As intended in the world we all live in digital space and physical space. It's really digital space. So again, no signals and no noise. And that'll give you what? Basically, when you have no signal, no noise, get one more. No noise, no signal, no noise, or what? Try the one. No signal, no noise, and no noise. So two no noise equals a stop. A noisy start. Two noise. Basically, any noise, any combination of this noise and signal. Think. One noise, one signal, one noise. No noise. So you get noise. Now, basically, this time is experiencing a lot of entropy. System can deal with that kind of problem. You have to take some additional space to handle kind of system dynamics that's happening in the fluctuation field of the information field or what's the person at that time. So guys, the noise protocol. So noise protocol is like make noise because if you don't make noise, you have to shut down our whole system. Basically, just the system structures can implode. The system can implode its own weight, explode its own weight because it's doing too much with too many resources. Yes, too much space. But he has too much space and doesn't have enough time. He has too much time or doesn't have enough space to store it. Kind of duality, resource duality. Or he has double the space to the time and double time to the space to do it over the auxiliary BN or one of verification protocol. And get no noise, no signal, no noise. And what you get no noise. Basically, just 4 main states, but 3 main states. No noise, no signal, and noise. So you get the combination of this. So you get noise times noise. Noise times no noise. You can get noise times noise, which is noise cubed. Basically just include the system. So you have to get that to the part. So you have to use one as a state, as a still state, and that will be noise times no noise times no. You can use noise times no noise, which would mean a noisy medium. That's what it says, noisy medium. That's noise squared. You get a channel where you can get some information out, but that information just starts to output some noise before you get information out. But come and stay still state. It's a medium protocol. It's a still. It means like it's actually on sparse. It's where it's really well. But until we measure it, it doesn't give us any noise. There's no noise until you measure. Until you look for trouble. You get signal, no signal, and no signal is like literally you don't get information. So the same kind of thing. So you have to lose. Basically, you can lose it like Yango. So if you have no noise first, and then no noise can be no signal. If you get noise first, you get no signal. You can use it to start and stop a system. That's what it is. If you get noise first, you can use it to send information, entropy into the system, to propagate as a fluctuation, to trigger some kind of space, some kind of arbitrary, some kind of chain that you control, encoding the lepton field into it. Basically, you get something you can do before you can start the computer. That's what it says. But those noises are just like a random sequence of random like some kind of a signal the computer understands, like a digital push. Like a digital push. If you push it, if you like you can show the computer with just no touching from a which is Wi-Fi. That's what I'm saying. Kind of thing. You can turn the computer with Wi-Fi. That's what I'm saying. Basically, this computer can turn on Wi-Fi. You don't have to turn the computer on, or just walk into the room and see your face. It turns on. It's not that scary. It's just really basic stuff. But you have to understand Fourier series a lot, and that's why I'm working on it. Because I want to turn on two computers, but I lose just turn on one computer, like a master bomb. I want to do wirelessly, and that's what I'm going of. I'm still using this kind of a system. Yeah, I made some here. Oh, so this kind of the constant C, but this n is 10. This n is 10. So this n is 10. So this is noise. But this constant v x is 1. But because 1 doesn't change, so it sees a constant I don't really know what it changes to. But okay, C is 1. But this 1 is 10. But this 10 is 1. Just to get table of values. So we get table of values. So we get A. Oh, so A is nothing. So you can't have A. So the table of values is let's do 20, 25. Oh, 25. X is 25. So x is 25 is 25, but x, y, x axis, y axis 1 to 1 zoom mode. So you get this kind of f of x, but f of x is a function of x. But a function of the function of x, f star. The three graphs I love, but it's so you get a kind of system here. Differential if you do a definite integral. Oh, I can zoom in. I can zoom in. I don't even know I can pan and zoom. I don't know. That's why you come to this and learn. But don't teach you like in this, like in class. Like, don't teach you classes. Like they don't teach you how to use the system here too, because the classes don't go that only like it. But listen, this is what I'm saying. Basically, you have to try the model. So if you have noise, if you still have a noisy start, you have to get a signal out. You can't use a signal. You have to cut the switch. It's like if I'm starting something, I can't literally just because I'm holding a noise state. Noise state is just have to go. Basically, I have to let go of that noise. It's like if I'm holding if I'm holding a weight on my hand, like a big weight, a small weight, two equal weights. If I'm holding something 10 kg on left hand, my left hand is stronger because I'm left-handed. It doesn't matter who my left hand. I'm holding one left hand. It doesn't matter the weight. There's no equal. Just my hand is what's it? If I'm holding a weight on one hand and holding an apple on the other, and I drop the apple first for the weight. It doesn't make any sense. Basically, it's just to do something as a gift. Basically, it's a system. So if I have if I have two weights, 150 kg and one 5. You can definitely and my hand is not strong enough to hold the 10 to 50 kg. I have to give the 5 if I want to keep holding the 5 kg, I feel 50 kg. If I want to keep holding 50, I have to give the 5 but in a time frame. That's what I'm thinking. This wasn't a potential question. So literally, just what it does. If I'm holding one weight, one state, one game, one active state, I'm holding something like an artifact in space. You have some space. You have some allocated bytes ahead of time. Let me try and calculate. So this is what I'm saying. It does it. So the area is say I'm holding 50 kg. 50 kg is what? Divided by 10 seconds. In 10 seconds, I will hold 50 kg just upright on my shoulder, right hand like this. 50 kg divided by 10 is 5. 5. Now, 5 seconds, wait, 10 seconds is what? 10 seconds is what? 10 seconds is what? 10 times 5. But not 10 seconds, 60 seconds. Mix them in. Let's make 60,000. 60,000. That's 1 millisecond. 600,000. Basically, I'll get 50 kg. Let me just go here. Actually, 50 kg divided by 10 seconds. This will give you 5 kilograms per second. Now we're gonna put 5 kg. 5 kg divided by 10. So we get basically this one I'm saying 5 kg divided by, so you get 5 kg is 0.5 kilograms basically. So this is 5 kg. So you get something else. So basically you get a balance in inequality, and equation must resolve itself via a potential differential equation. You don't want to resolve this as a traditional Fourier system. So you want to let go of the weight first that's holding you down, the one that's holding you most down. And that is what the pulling down. That's the 50 kg. So you keep watching. The more you watch, the more you hold it. So you let go of the. Going to share 10 seconds window at 5. I want to share when they reach 5 seconds. 10 times 10 is 100. 100 seconds. 100 seconds divided by 2 is 50 seconds. So the share 50 milliseconds. Yes, the share half of that is, so basically the share 50 seconds, 500 milliseconds. So we have so my new equivalent will be 50 milliseconds, 10 times 10, 50 milliseconds. So 10 divided by 2 is 50. Basically you get 50 milliseconds. The share, but this 15 milliseconds just kind of wait. I'm doing very poorly, so this kind of thing I'll just do it properly here because I just go from basically the 52 milliseconds is the time or share. Stop, Alexa. For my last one, I'm done now. So this 15 milliseconds is the time that will share, and this 15 milliseconds is like divided by 2, so they cannot validate that 15 milliseconds gap when they have the jerk. The jerk is the total distribution of the space and the area, because that's what the pressure can happen. If they violate that system, the noise will be the signal, and it's going to be the noise, and you get kind of a duality and get information via the product, because you don't know what you're looking at anymore, because you got to basically when you have the wave noise, you basically gotta let the system implode. And this is how the micro OS starts up. You literally just give up one thing. Where you give up when I'm trying to flash this on the hard drive. This kind of a thing, I couldn't find the DCU power, but this one I'm trying to flash my own signal. So this is a hard disk, but I just stay hard drive. This is like a Hitachi disk. Here, I love this disk, but I don't like it. I love it for now. Don't do a bitch. Yeah, but listen. It's gonna be flashing. That's how it works. So you have to let go of something. Whether you have 2 hands or 3 hands, but you got the something always observing that state, and that's like the kind of tracer function. Based on the standard model theory of calculus. What's the time now? My clock is done. Thank you. So, like I was saying to you, I'm gonna end this video now. But like literally, where was I? So basically, this is kind of way to do it, but it's like that. So this kind of thing, you can jumpstart system. So it's basically a jumpstart system for still system. I love this kind of thing because it can use jumpstart system that's very old. Jumpstart the car, but I don't jumpstart the car that's not mine. But without any wires, that's kind of the key thing. You jumpstart something that's not yours, but you don't need a single start. You just need enough noise first via the area. Basically, you have a area you have of the waveform, and that'll be polarized to the car. Or with the starting wires literally, and you put enough juice in it, and that juice will be the space that the wave program until before noise clears. You then so you have basically you then have half the time to start again. So you then have to fire the actual start instruction. Okay, so you have the dimension of the space. So you have the space. You have like 180. So 180 is the dimension of the start, but you have to halve that dimension. So basically you take the half of that dimension, which is space you have already, and that'll be a star signal. That's what you can put in a star, which is like the kind of this one is like where the wave is gonna be the area, but you're gonna have some of another area of space number of time window they can use to start it. Because you used to basically work in a synchronized way, and that's why I love Fouriere. Thank you guys. Because it's a very powerful framework for like hacking, but I'm an ethical hacker. They will say.